All right, it's time for us to continue with our model. We're going to continue to work on calibrating it. The last thing that we talked about was looking at the probability of clicking or not on a summary. All right, so let's move on now to, let's try to figure out in our model, how long will people spend looking at a document? So what is the time to view a document? So you've decided to click, you go to view this document. It's displayed in your web browser. You're going to be trying to decide, is this a relevant document or not a relevant document, so that you can save it, or you decide it's not relevant and you decide to hit the back button. And then you're back and you continue and you're looking for more relevant documents. So, there's lots of things that we could consider, with regard to how long you're going to view a document. But look, what's really important, and one of the things, but we do know the length. All right. And we know that the length is a very important thing to how long is it going to take you to try to decide whether it's relevant or not. In particular, keep in mind the notion of the way we're thinking about relevance as assigned in this task, which is we think this document, we clicked on it because we think it's relevant. Now let's go find and confirm and make sure that this document has the relevant material in it. You might have to look quite far in that document. You've gotten these nice little query bias summaries, so you should give a sense, oh yeah, it's somewhere in here, but we're not given too much help in finding the relevant material in a document, so we might have to read a fair amount of it. Now, sometimes certainly you get there and you read a bit of the page and you're like, oh, I don't know why I clicked on it, and yep, that's not relevant. So you could give up pretty quickly, possibly. But let's go ahead and we're in the world of keeping things simple. Let's use length and see how well this works and what can we do with it. And so what we're going to do is we're going to record the amount of time people spend looking at these documents versus its length. And we're going to fit a line, so do a linear fit to their first viewing of the document. And what do I mean by first viewing? Well, there is in our collection duplicates. Now, these are not exact duplicates. These, because if they were, we would have been able to that wouldn't exist. What they are is the newspapers, they often do updates to stories. And we end up with several of these, and something has changed in them, but then they all show up and our users see them. It's another relevant document, but they've basically already read it, so they're not really going to have to spend very long to look at it. So their time on a duplicate document is quite different than the first time that they see a document of this. And what we've done is we've taken the collection and we've searched for near duplicates in it, and we've identified the near duplicates. And with these near duplicates, then we're able to separately model the documents the first time that they're seen versus latter times that users actually see them. Now, we have a nice slide of this in the presentation. I don't have fancy video to be able to transfer over. This is slide 22 in the PowerPoint presentation for the time bias gain. And what you see here basically, so we've got a y-axis of time in seconds. And we go from 0 up to a minute. And we measure document length. This is, we've run our tokenizer over it, and we have our words. We've broken it up, and we can look at documents. There's some really long documents in the collection, 2,500 words. So we can look at these guys and so forth. All right. But basically what we see is largely a line that when fit is about like this. All right. You know, and of course you'll see the individual points. There are more points for the shorter documents because there are more shorter documents than a few out here. These are actually, these are not individual data points. These happen to be in the picture. You'll note that we report that there's actually a total of 4,212 data points. And so it's actually really quite noisy that have been averaged for the visualization. That is not what we do to fit. We're not using these averaged points. The fit is actually on the full set of data, but this is just so that we can see. Otherwise, there's too many data points. And then we have this other line here that we just decide is a fit for duplicates, and we use little plus signs to represent when people view duplicate documents. And basically the thing that we noted was no matter what the length of a duplicate document is, basically people spend a constant amount of time. They look at the page and they're like, yeah, I've seen that document already. I agree. I save it as relevant. Okay. They don't read it again. But in general, we see what can be it's a reasonable approximation. The longer the document, the longer they spend looking at it, trying to make their decision. But even for these super huge documents, we're out, no longer than about a minute on average, basically, because this linear fit is giving us an average for our population of users for how long will they spend looking at a page based upon its length. And remember, these are documents that they clicked on because they thought they were going to be relevant. They do take some time to figure out and make a final decision about whether it's relevant or not, and it does appear to be based upon the length. Now, after we get that fit, we end up with the following model for the time that someone spends on a document to read it, and it's got some length in words, and our model ends up saying we get a 0.018. This is this is actually seconds per word. Multiplied by our length. All right, plus a constant time of 7.8 seconds. All right, so that's basically the y-intercept. And we report also then how do we deal with duplicate documents. And I think what we might have done, I wish I actually remembered. I think we might have just said duplicate document we take as 0 length, and we say that there's 7.8 seconds. But we might have also separately fit that and come up with a value for just a single value for the duplicate documents. I do forget. It doesn't really matter. It's approximately, you can see from the plot about that. All right. So this gives us our model. So when we are going to basically figure out in a sort of simulation notion, you're viewing this document. How much time do you spend there? There you go. All right. So what's next for us to figure out in our model? We need to know about when someone actually looks at the document, do they decide whether it's relevant or not? And so this is simple. It's, again, we just do a bunch of averaging. And so what's the probability that the user will judge it relevant? This is the same notion as saving the document. given that we have a judgment from NIST that it's relevant. So this was our primary assessor. These people are not exactly the same. We're using this as our signal about whether we think it's relevant or not, and to what extent will they then think it's relevant. And what we get is when it is the probability they'll judge it relevant when it's relevant is 0.77, and the probability that they will judge it relevant when the NIST assessor thought it was not relevant. So someone looks at a summary, again, there's some probability that they're going to click on it even if the NIST assessor thought it wasn't relevant. And then there's still some probability that they actually might decide, yeah, I'm going to save it as relevant. They think it's relevant, even though the NIST assessor didn't think it was relevant. And this happens to be probability 0.27. So again, we see the same trend, which is people are absolutely more inclined in the right directions, but it's not 100% and 0%. Because there's not perfect agreement. These are not the same people. They don't have the same backgrounds and contexts and so forth and so on. All right, so we've got quite a few pieces of the model figured out. Now we need to talk about how long it is, okay? How long do you actually spend doing your search, okay? Well, it's as follows. Here, what we did is, we ran this user study, and if you remember, I said that we go and we had people work for 10 minutes. So we fixed the amount of time that they work. We don't have an estimate from the user study of about how long do people work at this task. And so what we did to find out people's time to search, so how much time do they dedicate to this? What we did is we had access to an export that had been made available to researchers. It's all anonymized and stuff, and we don't know who had done any of this, but this is some basic stuff from a Bing search log. So we don't even know the queries, by the way. So we don't know the queries, we don't know the people, we don't know the URLs. It's just that we know that they did searches and they clicked on a certain number of documents. So what we had were in this from this Bing search log that we had access to. Again, no personal information in this at all. What we did is, again, we were trying to model an informational search where people really wanted to find lots of stuff. So we took the searches that had 5 or more clicks on them. So that's a lot of, I want to find relevant documents. I'm clicking on lots of things. These are very engaged people. This models, again, we're working with Trek collection, and the idea would be that these are people wanting to find lots of relevant documents. This is sort of in the model of the existing Trek. And so we're going to model our users in the same way. So this is 5 or more clicks, and we limited them to be sure that they did actually spend on their total task time less than 30 minutes. All right, we wanted to cap that. There's all sorts of stuff when we deal with web data with gigantic outliers, strange things in behavior. These could be robots, these could be other behavior that's just out of the ordinary, and they can skew systems and the fitting of models. And so sometimes it does make sense to just put some hard truncations on the data set. Now, when we do this actually gave us a lot of data. And what we did in the time for the in the original time bias gain work, the SIGIR 2012 paper. So you'll see we go from 0 to 1500 seconds. And we have here D of T. All right, and so what this is, from 0 to 1, this is the fraction of people working to time t. So basically, and so this is the fraction, and what we're interested in, I guess this should be the title of the plot, but we're like, what fraction of the people are still working at these points in time? So how many are still working at 500 seconds? How many are working at 1,000, 1,500? And it ends up that for this data, an easy fit to do that seemed to work pretty nicely was exponential decay. All right. And so we did a fit of this, and I won't try to show on this the users, which is a solid line. This is slide 12, by the way, in the presentation. So slide 12, but they're very close fit. And what we ended up with was an exponential decay with a half-life of 224 seconds. And so this, I'll just write it out up above here. So we can determine sort of this decay function, or a survival function, so to speak, of what's the fraction of people that are still searching at a given time, with an exponential of e to the minus t, where t is time in seconds, natural logarithm of 2 divided by h, where this is the half-life, all right, which was equal to 224 seconds. Now, in latter work that we've done, we've actually found that this is better fit by looking at a log normal fit to the data, which is the time spent searching. So we can fit the time that people spend searching, which forms a log normal distribution. Log normal distribution, we have time, and this is basically numbers of people. And what we see in a log normal distribution is it basically looks like something like this. And so you end up with these long tails. And the idea is you take the log of this, and then you can fit a normal distribution to it. And so this is not the decay. This is the distribution of time spent searching, and you can fit that distribution, and we can use it in a different version of the model where we simulate the amount of time someone spends by drawing from this distribution a random deviant, and then saying, well, in our simulation, this person's going to work for this amount of time. So that's some future work that we had done, or latter work after this. But, very much you can just understand it for the most part as most people should search for a short period of time, and then you've got this longer tail, basically, of people who do engage in very long searches. With a half-life of 224 seconds, 300 seconds is 5 minutes. So, people are searching, less than half of the people are done searching at 4 minutes. Okay, and this is people that we modeled who had done 5 clicks. So, really, they're spending, less than a minute per document or so, which actually is quite similar to what we saw when we looked at the amount of time people spent to try to decide whether they had something relevant or not. Certainly, there are people who could spend a large amount of time, and they might spend it because they click and they read the whole document. They're not just trying to make a decision whether it's relevant or not, but they're spending lots of time actually reading it. So there's a lot of variation possible in the system depending upon what the users are actually doing. All right. So what we end up now with is a notion of, all right, we've got all this stuff to model for the users. We found out whether they're gonna, what's the probability of them clicking on a document given the NIST judgment of it being relevant or not. We have the probability that when they get to a document, Are they going to decide whether it's relevant or not? We've got the amount of time that they spend looking at a summary, which we just fixed it at 4.4 seconds based upon the modeling of the data. And then we've got a model for how long they're going to look at a document, but that is dependent because it matters so much on the length, because of the variation in the length of the document. All right, so we've got those times, we have those probabilities. This then allows us to end up estimating and basically putting it together to say, how long will it take someone to reach a certain rank in the list of results? So the people are working down in the rank list. How long is it going to take them to get to, say, rank 5 or rank 6 or even rank 20? All right, so we end up with this equation then. So we end up with the time to reach rank K. So this is rank K. This is how long is it going to take you to get to that rank? This ends up being a summation from rank 1 to K minus 1. And we do T of S, which is our time spent on our summary. Okay. Plus T of D on the length of document I. So the document that we find at rank I, so in that list. So again, we plug this, our formula, we go and we take that document, we count how many words there are in it, and then the formula then gives us our time. So we've got how much time do we spend on this, how much time we spend on the document, but we don't always go to the document. So we multiply that by the probability of, do I click on it or not? So the probability that I click on it, given that it's relevant at I. And there's another parentheses here to finish this off. All right, so this gives us a way, it's quite simple. It's basically, yeah, I'm working down the rank list. I'll spend this amount of time per summary, and I'm going to basically, this is a population average where we're saying, yep, we predict that if you were to click on it, you would spend this amount of time. And so what's the probability that you actually click on it? What's basically the average probability that people are clicking on it? So this gives us our expected time, which is basically the average amount of time that it's going to take our population to reach down and get to rank K. So this lets us estimate how long it takes you to get in the rank list. We're going to be able to combine that with our notion of how long do you actually spend in the rank list. All right. Great. So this is time to reach rank K. All right. So we can now plug these together. We've got time to reach this rank, and we had our decay function. So now what we can actually do is we can say, all right, we'll take our decay function, which again was the fraction of people still searching at a given time. We can take our time to reach rank K, and then this is going to give us back the probability or the fraction that are still searching at rank K. So now we've been able to turn it into, from just times, we were able to plug in ranks. And so, we can ask questions about at this rank, how long on average, which tells us the fraction of people still searching. All right. Now, our goal was, we want to be able to estimate the number of relevant documents people are finding. That's our notion of gain, so to speak, that people are going to accumulate. And it's a very concrete thing. I'm accumulating number of documents. It's not an amorphous notion of gain that doesn't make sense to sum together. It's a very solid sense. It's a very concrete thing. All right, so the average amount of gain at a given rank, so for rank K, is, we'll say and this. So again, gain. Let me be clear. This is number of relevant documents found, or if you want to call it saved, that the user has decided to save. All right. So gain is this is the number of relevant documents that we're talking about here. And it is the probability of clicking on a summary, given that it's known to be relevant. That's known to be relevant as per the NIST assessor, multiplied by the probability of judging it to be relevant, given the relevance of the assessor, okay, given that it's known to be relevant from the assessor. All right, and this is what we say the gain is if the document at K is relevant. So for the documents that we have, our assessors have judged to be relevant, what fraction of them are our users going to be saying are relevant? Then we go ahead and we set that the gain is 0 if the document is not, so the document, we could say document at K is, I'll just spell it out here. If the document at K is not relevant. All right. Now, this might seem a little strange. Why do they get 0 gain there? So if we don't do this, we end up with this strange notion, which is, what does it mean for the assessor to have made this judgment and decide that it's relevant when not the assessor, our users, when we don't actually believe it's relevant? We can end up with this notion that, take for example a list of documents that come back and they truly, absolutely are 100% not relevant at all. Now, when we have a model here where we're simulating human behavior, and our model of this would then say, if we gave any gain for those documents, that in a 100% not relevant list, that these users would slowly, as they work down that list, accumulate, they'd be like, yeah, they're saving relevant documents. And what we're really saying is, yeah, because people make mistakes, we think that even the world's worst search engine that only returns non-relevant material will still have this growth in value. And that's actually not realistic. If it's truly not relevant, you should get 0 as the score for finding and saving relevant documents. So this is really a fix to our modeling of our user. It would be great if we truly had a way to model users and to know whether or not they actually can make a true decision of is it relevant or not. But if we could do that, we actually wouldn't be in this business, because if we could truly know whether people would judge things relevant or not, that is the technology we would use to make their search engine results, because then we would find them only the stuff that they thought were relevant. So we can't really do that. Maybe there's something in between. Maybe we could have some sort of estimation or something that it's not always just a 0 for the things that the NIST assessor said were not relevant. But I get a sense that we're a ways from that. And so for now, this is a good fix to our modeling so that we don't accumulate the notion of saving relevant documents when we know they're absolutely not relevant. That would be a sort of a gross mistake in the modeling to have it function that way. So this is a safe notion. We say this happens and they're going to get some they're going to find these relevant documents, but we only let them find the ones that we agree are relevant. All right. Now, so we've got the notion of how long does it take people to get to a certain rank. We can figure out the fraction of people that are still searching. At a given rank, we can figure out what on average will the population be saying and be getting rewarded for finding a relevant document or not. So when we put it all together, we end up with the following. So we have the total expected here is a fancy word for average. So total expected gain, and again, gain is, I'm going to put that in parentheses and say total expected number of relevant documents found for a ranked list of results. We can compute this as a summation as we go down the rank list to, we've got a list of results from our search engine and we only produce them to be so long. Often we'll do like 1,000 results, okay? So whatever the maximum rank of the results list is, so we're going to evaluate a given results list that's been ranked. We're going to go down from the topmost rank 1 on down through the rank list, and we're going to sum up the values. And so we go G of K, which again, that's the fraction of relevant documents found by people on average, which we have shown on the previous, well, do we not have a previous slide, previous whiteboard before I erased it? And then that's multiplied by the fraction of people who are still searching at that point in time. Because we're able to go and say, oh, well, at this rank, how much time has gone by on average for people? And this will tell us the fraction of people. And then we get this nice summation. Very, very nice. Now, that puts it all together. We started with our observations of users. Now we have built our model, we've calibrated it. Calibrating means, again, to set what the parameters. So that's the parameter like the half-life and the decay. That's the parameters for our linear fit for the amount of time spent. Those are the parameters for the probability of clicking and the probability of recognizing that a document is relevant. All of those values are set or calibrated from looking at actual data. Okay.